Okay, so hi everyone, this is Ayush, and today we are going to discuss find peak element LeetCode question. Uh, this question was asked in these many companies, as you can see the list on the screen, and companies like Amazon, Apple, Microsoft, Yahoo, Nvidia, like lots of Flipkart. Yeah, you can see the whole list on the screen. This is very important question in terms of interview. Let's see how do we tackle this question. Let's read the problem first, and then let's see. So a peak element is an element that is strictly greater than its neighbors. Given zero index integer array nums, find the peak element and return its index. If array contains multiple peaks, return the index to any of the peaks. Okay, so you may imagine that nums of -1 and nums of n is negative infinite. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. You must write an algorithm that runs in O of log n type. Okay, so this is a problem statement. Let's try to understand it by example and how what is peak and how do we find it and all. So let's switch to the iPad. This is our array. This is our example. So basically what question says, firstly in the note it says that if I'm the left neighbor of the zeroth element is basically -1, right? It is out of bounds, so we are considering our last element, the element just before our zeroth element, to be negative infinite, and element just after our last element to be negative infinite as well, right? In this case, ninth element. So basically if we go out of bounds, we are considering out of bounds as negative infinite. Okay, so what is peak here? A peak element is basically if my nums of I is basically my peak element if my nums of I is strictly greater than nums of I minus 1, and it is also strictly greater than nums of I plus 1, right? This is the condition for peak element as per the question. Okay, so what is the brute force way to do this? A simple brute force way, as you can see, is just we traverse element by element, check its previous element, check its next element, and see if this condition holds, then my ith element, nums of ith, this element basically is the peak element, and we would return it, right? Okay, we have to return the index to any of the peaks, like multiple nums of multiple I can satisfy this position. We can return any of the index, any of the i's. Okay, so what is the brute force way? I would traverse the array from left to right or anything, and just check the previous element, I minus 1th element, and the I plus 1th element, and check is this condition holding or not. So in this case, basically if I'm at 0th position, I'll check the previous. In this case, the previous does not exist, so I'll consider it to be negative infinite, and the next to be 4. Is my 1 greater than negative infinite? Yes. Is my 1 greater than 4? No. So this 0th element cannot be my peak. Let's move on. So this is my I now, this is my I minus 1, and this is my I plus 1. Is 4 greater than 1? Yes. Is 4 greater than 7? No. 7 is greater than 4. So this basically first index also cannot be my peak element. Let's move on, and now we are at basically I equal to 2, and here I minus 1 would be 1 and I plus 1 would be this. Okay, so now I'll check again. Is my 7 greater than 4? Yes. And is my 7 greater than 6? Yes. So I can say that this condition holds. This condition holds, and 7 is my peak element. And I can just return this index 2, right? This is the brute force approach. In worst case, now we have found the answer, so I can just return, we can stop our search here. But in like worst case, you might find your peak element to be at last index, right? The last index, or like very at that very end of the array, right? So you would have to traverse each index iteratively. So you have to traverse in this way, and in worst case you have to traverse all n elements, so it would give you O of n time complexity, which is linear time complexity in our brute force approach. So can we optimize this? Yes. How do we optimize this? Okay, in this case, as you can see, that array is not sorted or anything. We don't have an sorted order already. We just have something, just some normal array. We have to find a peak, and to optimize to log n time complexity, we know only one algorithm now, that is binary search. So how do we apply binary search here is itself indeed like case work, you have to think about it very properly. We will discuss this using cases, but to understand this, uh, basically in this case we are not actually using the sorted property of an array, but we are using our brain to understand which half to eliminate and which half can I find the peak. Remember, we are not finding a particular peak or anything. In this case itself, you can see that we have if this was mid basically, so we have two peaks. This one is peak, this is peak element, and this is also peak element, as you can compare the previous and the next element of both of them, right? So we have to find basically any peak. So how do we do it? Let's look at the approaches, let's look at the casework, and how are we formulating this. I'll make a bold statement here, that is, so for approach, for actually implementing binary search, we need to know which half to eliminate, right? You must be familiar with all the previous questions you did. You need an half to eliminate and a half to search it. So you should be like smartly able to eliminate one half or move to one half, right? So I am making a bold statement here. We will prove this by using cases. We will understand this, why this statement hold. And the statement basically is, for approach for elimination, move to the side which has greater elements. So I'm saying that if this is my mid, this is my mid plus 1, and this is my mid minus 1. If mid is not my peak, if nums of mid is not my peak, I will move to the side which has greater element. Basically, if mid plus 1 is basically greater than nums of mid, then I would move to mid plus 1. And if my mid minus 1, the number present at mid minus 1, is greater than number present at mid, then I'll move to mid minus 1 side. Why? We will understand this by casework. So let's do the casework. Okay. So I have made few cases here. Just try to follow with me. The first case, very basic and simple case, as we discussed in brute force as well, was basically if my nums of mid, this is the graph, you can assume that this is the x-axis which has indexes, and this is the y-axis which has nums of basically index, right? So this is the graph I'm assuming. Okay, and this line basically denotes the magnitude itself, right? Okay, that aside, so if my nums of mid is basically greater than my nums of mid minus 1 and is also greater than nums of mid plus 1, right? So it will look something like this in graphical format, which is like we are calling this peak, right? And if this condition holds, like the condition, this one, this is basically the case I have like drawn here. If this is the case, then I can just say we have found the peak. We have found the peak. We don't have to search anymore. I'll just return this index, mid index, and I'll terminate my search. Okay. So what's the next case? Okay. This is a very simple basic case. Okay. This is like very fine, a simple basic case if we return. So let's move on to the next case. So this is my second case. So what I'm saying now, let's focus here, like 2a. This is my mid, nums of mid now. This is my nums of mid plus 1, and this is my nums of mid minus 1. So what I'm saying is move to the element which is greater. If the mid is not the peak element, then move to the side which has greater element. So in this case, like if we move to the right side, as we know that nums of mid plus 1 is greater than nums of mid, as you can clearly see in this diagram. So I am saying move to the right side, as right side has a greater element. Why? Okay, let's understand this. If I move to the right side, you can see that eventually I can have my mid to be here, right? I can find my peak. Makes sense? So this half consists of peak. So I can search in this half. Basically, if there is some increasing element, then it is bound to have a peak. Either this would keep on increasing, the right side will keep on increasing and then decrease, or the same case here, the right side is greater, right, and it is increasing and the array ends, right? But even at the end, as our question mentions, that even at the end we have a negative infinite when we go out of bounds. So after the last element we have negative infinite, which would be something here. So this is our last element, would be our peak. So if we move to the greater side, it is like bound to happen. We will find at least one peak there. Why? In this case, in this A case of second A, you can see if we move to the increasing side, it may increase up to a while, then may decrease. So definitely I can find a peak in right side, right, if it decreases. Okay, even now let's look at the 2b case. Even if it does not decrease, even if it does not decrease, we would end somewhere. We would end at a larger element, right? If it is monotonic, like in this case, just consider this part. If it is monotonic and keeps on increasing, it does not decrease somewhere like this, then it keeps on increasing, and the largest element would be at the end of the array. The largest element relative to this, right? Then you can say the last out of bounds element is therefore negative infinite, and it is greater than the previous element, it is greater than the next element. So this would be your peak, this would be your peak, or this would be your peak. So what if you're saying me we can move to the left? What if in this case we move to the left? You can see that elements keep on decreasing. Even if you land any position, the next element would be always greater than your previous element. So you cannot guarantee that you can find a peak in left half here in this case specifically. So if, and even if and what if you say if there exists a peak? Okay, I am saying if there exists a peak, so it might look something like this. Here we increase and then decrease again. Okay, then we move to the left, and you can say that can I find this peak? Now if you can find this peak, that's fine, but you cannot guarantee to find this peak. You move to the left, you land here, you found the peak, you return the answer. Okay, that's fine, but how would you know that this peak exists? Basically, moving right guarantee in this case of like increasing pattern, I can guarantee that there is a peak. Definitely there is a peak. If there is not a peak, we'll reach the end of the array, and automatically like last element would define the peak itself, right? If it is greater than previous last. So I can, if moving to the right can guarantee me to find one peak, so I'll move to the right in this case. In this case, if we move to the left, okay, we might find this peak, but we cannot, if this was not the case, if it was simply decreasing, we do not have a peak there. So I cannot guarantee to find the peak here. Even if I reach the last element, I agree that last element would be greater than the negative infinite when we go out of bounds, but it would be still lesser than my next element, right? So this is not the peak. This is not the peak. We cannot guarantee finding a peak if we go to the element which is decreasing in the decreasing side. Okay, got it? Let's try to understand using the same case but flipped. Okay, so in this case, as you can see, this is my mid, this is my mid. Let's focus on 3a. This is my mid, and now my increasing side, is basically the left side, right? The left side is increasing. Now if you move to the right, you're not guaranteed to find the peak because you would keep on decreasing. You can land on any point here. The last would be like negative infinite after the last, but even if you land on any point here, as you can see, you won't find a peak. Just draw the graph, you can understand it yourself, because the left element in this portion, basically the left element would be always greater than the right element. The previous element would be always greater than this. Even if you have something like this, even if you have the peak, you cannot guarantee that a peak exists. But if you move to left, basically in this case, you are guaranteed to have a peak. Here. Why? See, if you move left and there exists a peak, and after like having a binary search to search here and move like to the increasing ones, we will eventually end up here, as we are moving to the side which is increasing, the element to the side which consists an element which is greater than our mid, right? So in this case we can find this peak, right? Or if the peak does not exist, like in this case, the b version of b part of this third case, so even if you move to the increasing side now, and there is no like actual peak you can see here like this one, but the last element is bound to be greater than the the first element, the zeroth element would be bound to be greater than our one element, right? And after at -1 we have negative infinite, so we have this peak. We are guaranteed to have a peak if we move to an increasing side, right? In this case the increasing side is this, and in this case the increasing side is this. You can look at these cases, think about it, and actually see why it is working. You have to think about it. It is not very intuitive at the first try. You have to understand these cases. You have to understand why we are moving to an increasing side, not a decreasing side, right? And the last case would be just this, this 4a. The mid is not the peak, as both of its previous and next element are greater than it. So now you ask me, where should I move, Ayush? The both of the sides are like increasing than it. Then how do I eliminate, right? Now in this case I'm telling you, you can move to any half. You can move to any half. Like both of them are increasing, right? So move to any half. It doesn't matter. If I move to right here, I'll eventually get a peak here, right? And if I move to left, I'll get this peak. You can move to any side if both of the neighboring elements are greater than our mid. Okay, so that clears up why are we like doing this, why are we moving to the increasing side. Things would be more clear, like we'll discuss the same example as we discussed in our brute force by applying binary search there. Before that, let's look at some edge cases. So edge case number 1 would be, we have single element in our array. So as question specify, at index -1 we have negative infinite, and index n also we have infinite, negative infinite. So basically this element, the single element itself, is a peak, as this is our structure. Make sense? If you have single element array, just return 0. This would be a peak element itself. So now in this case, like consider the second edge case. We are talking about the element which is at 0th index, and the element which is at n-1 index, basically the first and last index. Okay, so I'll just say, if my element, the 0th index, the number at 0th index is greater than my number at first index, like this is the case. If this is the case, then I can say that my index 0 is peak, right? And if my last element, like this is the case, if this is greater than my previous element, the second last, it is greater than second last element, then I can say, if this condition holds basically, then I can say index 2 is peak, right? Basically, to generalize it, index n-1 is peak, where n is size of array. Okay, I think the edge cases are pretty clear. So why did we discuss edge cases first? You'll understand it. Okay, so let's move to our example, and let's try to see how do we do binary search here. So let's modify our condition. Instead of I can, as we are doing binary search, I can just write mid here, and mid -1 here, and here mid +1. So if basically this condition holds, if my middle element is greater than these two, then I can say that we have found our peak element. Right, makes sense? So let's start our binary search. Before starting our binary search, I'll look for the edge cases. First edge case is that is my array has single element. Then I would just return that single element and just say that it is a peak, right? And secondly, if my first, the 0th element or n-1th element are peak elements, if this or this is my peak element, then I'll return it directly without like checking everything. So why are we doing this? Because we can have much simpler search space. Just we are doing this just so if we do a index -1 or index +1, we don't go out of bounds. I'm just doing this. You can do it your way, but I'm trying my search space to be as simple as possible. So okay, we would have our search space with index low at 1 and index high at n-1, right? Why? Because we have already considered this case. If either of the end elements are basically the peak elements, I would return it earlier itself. You don't have to do binary search then. And now let's do simple binary search. So This is my low, this is my high. What would be my mid? This would be my mid, right? So what I'll do is first check, is my middle element the peak element or not? So 3, as you can see, 3 is not greater than 6, or 3 is not greater than 5. So this is not my peak element, this is not my peak element, and okay, this is not my peak element. I have to eliminate one half. So which half do I eliminate now? I can eliminate any half. Now, like this is the case. This In this case, we are at the fourth case. As I said, if both of the elements are increasing from the middle element, are greater, so I can move to any half. I can prove it to it, you. So let's move to left half, right? We can move to any half. I'm choosing left half. So to move left half, I would update my high pointer to be mid -1. So let's update our high pointer to be mid -1. So our high would be here, right? And let's update our mid as well now. So now my mid would be here. Okay, is my mid now peak element? Yes, it is a peak element. So as it is greater than 7, as 7 is greater than 4, and it is greater than 6 as well, so I can just return this peak. Okay, so let's try this example now. First I'll check for the edge cases. Is my 0th element the peak element? No, as the next element is greater than this, as this holds. And is my last element the peak element? No. So these are not my peak elements. So I'll start my search with low equal to 1 and my high equal to basically here, right? So what would be my mid now? My mid would be here, right? This is my mid. So is my mid actually the peak element? No, as you can see, 3 is not the peak element, so I would have to eliminate one half. Now which half do we eliminate? As by the graph you can see that this is 1, this is 3, and the 5, right? The trend is something like this. So I would move to the increasing half. The increasing half is right side here, so I would move to the right side. Okay, let's move to the right. So to move to the right, I'll update my low pointer to be mid +1. So my low would be here, right? So my low is here and this is my high. So this would be my mid. So basically this is my mid, right? Now again I'll check, is my mid equal to peak element? No, as now 6 is greater than 5, this 5 cannot be my peak. So again I'll have to eliminate one half, as we still didn't find the peak. 6 is greater than 5, so the right side element, the next element, is basically greater, so we would move right as we discussed. So to move right, again I'll update my low pointer to a mid +1. So my low would be here now at 6 itself. So this is my low, this is my high, and this is my mid again. This would be my mid now. Okay, so at 6 I'll check, is that 6 my peak element? You can see that 6 is greater than 5 and 6 is greater than 4. So you can clearly see that 6 is my peak element, and I can just return it. I can return mid basically, right? So yeah, that's it in terms of example. Let's code it to understand it better. What am I doing? So let's move to the code. So before we code any binary search, let's consider our edge cases. Let's write down our edge cases, and then we can have our search space reduced down just by 1. Okay, so let's have n equal to nums.size, and if my n was basically equal to 1, the minimum size of array is 1, as you can look at the constraint itself. So if my n is equal to 1, you don't have to write curly braces, I can just return 0, right? If single element exists, if the array is of single element, then we can just return that element. If now I'll check if my first element is my 0th element or n-1th element the peak. So if my nums of 0 is greater than nums of 1, then I can just say my 0 is the peak element. Or if my nums of n-1 is greater than my nums of n-2, then I can just say that n-1 is peak, and I can just return n-1. Okay, these are the edge cases. Now let's do the binary search. So I'll initialize my low pointer to be 1 and my high pointer to be now n minus 1, n minus 2 actually, as we reduced our search space by 1. So while my low is greater than equal to high, balance threshold, so let's write down mid equals to low plus high minus low by 2. Right, now we will check if my middle element is peak or not. How do we do it? We can just do nums of is my nums of mid minus 1 lesser than my nums of mid, and then my nums of mid is greater than nums of mid plus 1. Now you are understanding why did we trim down our search space by 1 on each side. Just because, like, if I write mid minus 1 and mid plus 1 in this condition, I can say I won't go out of bounds. This is just safety check. You can instead of this, you can just do if else, like if I'm going out of bounds, then I'll initialize to negative infinite. You can do this as well. I find this approach pretty elegant because we don't it makes code clean and everything. So basically, this if this condition holds, I can clearly see that we have found the peak element. Peak found. I'll just return it. So I'll just return mid. Now if my now I'll move to the greater side. If nums of mid is not the peak, so at least one side would have the greater element, right? So if my nums of mid is like smaller than my nums of mid plus 1, let's say, okay, my nums of mid plus 1 is greater. So now I'll move to the right hand side. So to move to the right hand side, this I'll just write down the comment. If my next element is basically greater than mid, then I can search right. So to search right, I can just do low equal to mid plus 1, and if it does not hold, I can say my basically mid minus 1 element is greater than mid, so search left. To search left, I can just do high equal to mid minus 1. Make sense? So now if we don't find anything, I can just return an negative 1, but this should not run because we'll definitely find a peak. We are guaranteed to find a peak because of the constraints we have, because of the problem statement we have. Let's try to run this code. It should run fine, but let's see. Yeah, it runs fine. Let's submit it. Okay, the code got submitted, and yeah, and as we are implementing binary search here, this code is of complexity of log n. This is the most optimal approach, and we are not using any extra space, so it is of 1, which is constant space. So that's it from my side, I guess. And if you have any doubts or anything, you can just comment it out, and thanks for watching.